At a depth of 9.1 kilometers beneath Germany, there was no explosion, no collapse, no sign of disaster. The drill could still go deeper, but the temperature could not. With every meter drilled, the rock grew hotter, faster than the models had allowed for. And at this depth, the question was no longer, can we keep drilling? It became, if we continue, will this borehole still remain safe? There was no rushed decision, no panic, only a clear boundary that had to be acknowledged. Beyond 9,000 meters, there was no indication that the Earth was resisting, no abnormal vibrations, no voids, no escaping fat or fluids, only rock and heat. The KTB borehole was designed to go farther than any scientific drilling project before it, not to extract, not to exploit, only to reach. With every meter drilled, operations continued as planned. Drilling fluid circulated. The borehole walls remained stable, but the conditions surrounding the borehole began to change. Temperature rose steadily, then faster than the models had predicted. At this depth, heat was no longer a secondary parameter. It began to directly affect the stability of the borehole, the materials, and the ability to keep the well viable over time. At 9.1 kilometers, drilling deeper was no longer a question of how much farther can we go, but instead, can what we have already drilled remain safe? Before the drill reached a depth of 9.1 kilometers, stopping was not considered an imminent possibility. Not because of blind optimism, but because the numbers had already been laid out. Inside the project offices of the KTB borehole, temperature graphs stretching kilometer by kilometer had been drawn long in advance. Based on regional geology, laboratory measurements of rock samples, and heat flow data, engineers expected temperature to increase with depth, slowly, predictably, and within limits that existing technology was believed to tolerate. This was not humanity's first attempt at deep continental drilling. Before the main borehole, a pilot well had already been drilled. Measurements from that well showed no major deviation from the models. There were no early warnings, no clear breaking points. From a scientific perspective, continuing downward was the next logical step. Materials were selected to withstand high temperatures. Drilling fluids were engineered for extreme conditions. The casing strategy accounted for deep pressure. Even the target depth itself was not arbitrary. It was chosen with a margin of safety, a buffer between what they expected and what the technology could handle. The entire plan rested on a core assumption that the Earth below would continue to behave according to familiar rules, slow, stable, and within the boundaries described by the models. What those graphs could not clearly show was not a sudden thermal spike. It was something more subtle. Temperature began to rise, just slightly faster than predicted. Not fast enough to force an immediate stop, but fast enough to steadily thin the margin of safety. The entire decision depended on, and that margin turned out to be far more fragile than anyone had realized. The problem was not high temperature itself. It was the moment temperature began to interfere with everything else. At first, the increase in temperature remained within what was considered acceptable. A few degrees higher than expected, then a few more. On paper, it was not yet a problem. But deep underground, heat does not exist as an abstract number. At these depths, temperature begins to change, how everything behaves. Steel expands, seals gradually lose elasticity. Cement responds differently. When subjected to heat and pressure over long periods of time, materials designed to operate within a defined thermal range were now being pushed closer to their limits, not abruptly, but continuously. Drilling fluids, intended to cool and stabilize the well, had to work harder to carry heat back to the surface. The borehole walls, stable under earlier conditions, were now exposed to a combination of temperature and stress that could alter their long-term behavior. No immediate failure occurred, and that was the problem. Heat did not create a single moment of collapse. It reduced the reliability of the system over time. Every additional meter drilled meant higher temperatures along a longer section of the borehole. And with that came a question engineers could no longer avoid: not whether the well could withstand today, but whether it could remain stable for weeks, months, or years. At extreme depth, stability is not measured in moments. It is measured in time. A borehole that cannot be maintained is not merely difficult to study. It becomes a risk. At this point, heat was no longer a parameter to be recorded. It was actively shaping what could be done next. Drilling deeper would not simply extend the well. It would increase the thermal load on everything already in place: materials, casing, cement, and the borehole itself. The risk was no longer theoretical. It accumulated over time. And once that balance tipped in one direction, there would be no way to reverse it. The decision did not come after a mistake. There was no collapse, no accident, no sign that control had already been lost. The KTB borehole was still standing, and that is what made the decision harder. At that moment, the drill could still go deeper. Nothing underground forced an immediate stop. But the question had changed. It was no longer, how much deeper can we drill? It became, if we continue, what are we placing the future of this borehole on? Every additional meter did more than increase depth. It extended extreme heat along a longer section of the well, not for a moment, but for years. What had been built to withstand limits now had to withstand time. A deep borehole is not an achievement simply because it is reached. It only matters if it can continue to exist, to be measured, to be tested, to be understood. At these temperatures, no one could say for certain how long the well would remain stable. And that was the boundary, not the boundary of science, but the boundary of responsibility. Continuing to drill might have produced more data. It also risked making everything already achieved impossible to maintain safely. So the project stopped, not because going further was impossible, but because it was no longer possible to guarantee progress without sacrificing long-term stability. There was no dramatic ending, just a line drawn before everything began to slide out of control. The drill had reached its last safe depth, and this time, humans stopped, not because they were forced to, but because they chose to stop before going too far. They did not reach the limits of the earth. They reached the moment where understanding more had to be weighed against keeping what already existed stable.